I will give a survey of Mathematica functions related to solving algebraic equations in inequality, and I will discuss the choice of most appropriate solvers for various types of problems. So let me first summarize what types of solving we could identify. So one is complete description of the solution set for the system of algebraic equations of inequalities. The other is generic description of the solution set. Then finding some solution instances, finding the number of solutions, eliminating quantifier, and deciding existence of solutions. Global optimization and local optimization. So let me talk a little bit about each of these types of solving in turn. So for complete description of the solution set, so the two main functions, the most general ones, are reduce and solve with max extra conditions goes to O. So both those functions are basically doing the same thing, except that solve will represent the solution as a list of replacement rules, and reduce will return boolean formula describing the solution. And the other functions on the list are specific methods that apply to certain classes of problems, like Grobner base is the method used for systems of complex polynomial equations. Cylindrical decomposition is the method used for systems of real polynomial equations and inequalities. Root intervals, this just isolates roots of univariate polynomials. And n-roots is also complete description of the solution sets. So first, we get the description of the solution set as Boolean formula. So we get the variable and some bounds on the variable, equations or inequality bounds. Now the same solution set represented as replacement rules. So this is exactly the same set. The representation is different. So we get replacement rules for z because we solved for z, and we get conditions on x, y that make the solutions correct. Here's a picture of what we are solving. So this is a set that has two components. One is one-dimensional, the other is two-dimensional, and we get description of both components. So this is the one-dimensional component. These are two pieces of the two-dimensional components. This set is called Whitney's umbrella. And finally, we get intervals isolating roots of univariate polynomials. So we get a set of intervals represented as pairs of endpoints. And in each of those intervals, we have exactly 1 point. And this list here, it just tells us which polynomial has a root in this interval. We might have used a list of polynomials here, so that would indicate which polynomial has a root in the given interval. And for complex roots, same polynomial, we get all the intervals isolating all the roots. And here's a picture. So these are all the complex roots, the red points, the three on the real line here. And we see the isolating rectangles for the complex roots and isolating intervals for the real roots. Okay, the next class of functions is generic description of the solution set. So now we don't get all the solutions, we just get the almost all solutions, in the sense that the set of solutions that we miss has a lower dimension than the whole set of solutions. So here, solve without any options. This is the same Whitney's umbrella as before, except now the one-dimensional piece is missing. So the red lines are the pieces that are missing from the solution set. But the advantage of using this kind of functions is that they are faster than computing a complete solution set. And often we just want the generic representation, and the list of functions that give this representation. This is solve without any options, and solve Grobner basis with option coefficient domain goes to rational functions. So now if you put this option, then any parameters will be considered invertible objects, or any polynomials in parameters will be considered invertible. Generic cylindrical decomposition, so that this is something that can be used for solving real problems, real equations, the inequalities, getting the highest dimensional component. Linear solve has this property that it automatically generates the generic solution only. It considers all parameters to be invertible. And the roots function has also the same property. It will consider all parameters to be invertible. Next case, solution instances. Here we have functions where we have the find root function. So there's find instance, that's the most general function for finding symbolic instances. Find root will find numeric instances, numeric approximations. Linear solve, this actually is an instance finding function. It just finds, in the case where the matrix is degenerated, it will just produce the one solution. You need to call null space to get the full, the other component of the solution. And semi-algebraic component instances. This is something that is not so often used, so I will show it here. So first, find instance. So we have a polynomial. We are finding one instance where this polynomial is negative. And semi-algebraic component instances will find at least one point in each connected component of the set described by this polynomial being less than 0. So it gives the whole list of exact solutions. And here's the picture. So it was a row set, and the green dots are what we are getting with semi-algebraic component instances, and the red dot is the find instance output. Now the count roots. So we give it some particular equation that has a finite number of solutions, and we want to just count them, not find them. So this counts the roots of a polynomial, and you can see that the degree of the polynomial can be quite large. It can easily count the roots of this polynomial. This function counts roots of real roots of an x-block function. So this x-block function has three roots. And finally, we can count roots for holomorphic elementary functions in closed rectangles. We can count complex roots. So this function has 11 roots. This is by counting the winding number around the rectangle. So it has to be finite or bounded. Now, quantifier elimination. So we have a formula quantified with respect to some variable, and we want to produce equivalent formula without the quantifier, so eliminate this variable. So here are functions for quantifier elimination. The resolve and reduce are the most general functions, and then there are some specific functions. Eliminate and solve always. Eliminates an existential quantifier from a system of equations. Solve always a general quantifier from a system of equations. Cylindrical decomposition is what's used for quantifier elimination for real systems of equations and inequalities, and Grobner basis is used for system of complex equations. And here's an example. So resolve will try to eliminate quantifier with the fastest method, hopefully, but it will not try to solve the result. So you may get a system of unsolved equations and inequalities. And reduce eliminates the quantifier and solves the system, so you'll get something like this. Global optimization. So here's the list of global optimization functions. Minimize, maximize, min value, max value, argmin, argmax, the n versions of all those functions, and linear programming is also global optimization function. What I wanted to point out here is, well, for linear programming problems, computing the minimal value has the same cost as computing both the minimal value and the minimum point. This is not true for polynomial problems. For polynomial problems, especially if the constraints are strict inequalities, or equivalently, we are interested in just full dimensional subset of the constraint set, computing the minimal value can be much faster than computing the minimal value and the point where it's attained. So here's an example. We can get the minimal value, it's equal to this root object, and we can get it in less than a second, and the minimize here doesn't finish in 120 seconds. Now local minimum computation. So this is find minimum, find maximum, and the min value, max value, and so on versions of it. So here, find minimum finds a local minimum. It does not have to be a global minimum, so we get numeric approximation of global minimum here. See, it's smaller. And this is the exact value. With minimize, we can check that it's the same point as unminimize got. And here's a picture. We had a quartic polynomial, and the local minimum happens to be the one that's not global. So the one that's fine with find minimum. And okay, so now let me discuss some specific cases, like generic versus complete solutions. So reduce will return complete solutions. Solve gives generic solutions, that is, solutions that do not require equational conditions on continuous parameters. So in particular, if I was solving over the integers, the generic doesn't make sense really, so it's the same whether we use solve or reduce. Just the difference between Boolean formula and replacement rules. However, generic solutions can still be produced as conditional expressions because we may have solutions that are valid only if parameters satisfy inequalities. So we still have to give those conditions. So even from solve without any options, we can still get conditional expression output. Now we can, if we run this with solve without any options, this system has no generic solutions. We have two equations with some symbolic parameters. They have no equations. But in most cases, what's useful is we want to get the somewhat different interpretation what generic means. We want to get the solution that requires the minimum of assumptions on symbolic parameters. So with max extra condition goes to automatic, solve will do this. So it will produce the solution that requires, in this case, one equation. On parameters, there are three possibilities for these equations, and the solution always looks like this. And if we say max extra condition goes to all, we get all solutions, except that we get this message here that when parameter values specify these conditions or parameters are 0, the solution set contains full dimensional component. So basically, in this case, the equations become true if all the parameters are 0. And there is no way to represent this as replacement rule for x. So that's why it has to be given as message. So here's another case where we have full dimensional solution set. Now it's not all solutions, but we still, so let's see what the full solution really is. Its x is between minus square root of a and plus square root of a. This again cannot be expressed through replacement rules. That's why solve gives an empty list and a message. That's the downside of trying to represent solutions as replacement rules. Not all solutions can be put into this format. There's another particular issue is with the new solve. So in Mathematica 7 and earlier, we had this syntactic assumptions in solve. So equations that didn't contain the solve variable or variables would be treated as assumptions. And this would give two solutions, x minus 1 and x plus 1. Note that actually the solution minus 1 is valid if a is equal minus 1, and the other one is valid if a is plus 1. So each of them is kind of valid half of the time. And that's, so there are some problems with this understanding, with such extracting such type of assumptions. So first, we get different solution sets for logically equivalent systems. So if I added x to both sides of this equation, that we get the same system. But see, if we have a system that's less trivial system where that equations and has equations and inequalities, and it's a Boolean combination. It's really this kind of extracting assumptions. It's not really a good idea. You don't know where to extract assumptions from, and that's why Mathematica 8 doesn't have it. So if you do it in Mathematica 8, it will just treat it, okay, there are no solutions for it generically. You have to say max extra condition goes to automatic, then it will find the solution with the minimum number of assumptions necessary, and now it will tell you exactly what assumptions are necessary for the solutions to be valid. So one solution has a different assumption than the other solution. And what somebody really needs the functionality that was in version 7. One can get rid of conditional expression with normal, and the solutions are in the same form. Now, okay, another one, transcendental equations with symbolic parameters. So this is here's where difference between solve and reduce is more than just generic. Now solve uses non-equivalent transformations. Try to get some solutions fast. So we get this obvious solution that x is equal 2 to 1 over a. And now if we try to do this with reduce, it takes 8 seconds on a faster machine than this one, and the solution is kind of huge, even though it really seems to be the most innocent equation with one symbolic parameter that's not polynomial. So it's simplest transcendental equation with one parameter. But if we extract, so there are one thing is that we get more solutions. So there's infinite family of solutions. And second, just let's see where this solution is valid. So here's the picture. This solution happens to be valid everywhere outside those two circles. So there actually is some non-trivial complexity in there. And we can see that this is the solution. It's supposed to be equal to, but if we plot it, then it's equal to outside of something like 1 over e, and then it's kind of complicated function. inside those circles. So what I wanted to discuss here is exact versus approximate solution. So basically, we have methods for obtaining approximate solutions in two cases, either for linear equations, and especially a good idea of using approximate methods is if we have non-rational numeric coefficients. So here is an example where the coefficients are algebraically independent numeric objects. And if we look at timings, exact solving this is logarithmic scale. That's for exact solving, and that's for numeric solving. And indeed, if we take the size of the solution for exact solving, also logarithmic scale, you can see it grows pretty much exponentially, the size. So that's a case where using numeric methods is really better. However, we have to be careful because the numeric method for solving systems of linear equations can give wrong solution without a warning. So for machine precision, we get no solutions. This is a case where always there is one solution. With slightly higher precision, we get a two-dimensional solution, which is also incorrect. But with higher precision, we get the correct solution, and it's also very fast. So the other case where we have approximate method is polynomial roots. But that's about it. For all the other cases, NSolve will end up using symbolic methods, and therefore what I wanted to point out here is that using numeric coefficients when NSolve will end up using symbolic methods is not a good idea. So here's the warning message that says that NSolve had to rationalize the coefficients. But see, if in this case, NSolve cannot solve the problem because this evaluated, this no longer looks like 1/4 times 1 over logarithm of 2. And NSolve was not able to rationalize it correctly and get the solution. If instead of using 0.25, we use exact 1/4, then NSolve gets the correct solution. So what I wanted to point out here is that not a good idea to replace simple rational numbers with numeric approximations like this, if we may use numeric methods. So I guess I will finish here. Thank you.